Hi everyone, so this video aims to go through 2022 H2 Chem promo paper. So we're starting with question 1. We have two elements, flerovium and livermorium. So we first need to find the number of subatomic particles in the atoms for these two elements. So flerovium has 114 protons, 114 electrons. The number of neutrons is the nucleon number minus the proton number, 175. And we do the same for livermorium. So both protons and electrons are 116 and 176 neutrons. So statement 1, Lv plus ion. So Lv atom has 116 electrons. After it loses one electron, it will have 115. Flerovium ion is formed by gaining one electron for the flerovium atom. So it will also have 115 electrons. So statement 1 is true. Statement 2, deflection of charged particles in electric field. So first thing to remember, the angle of deflection is proportional to the charge over the mass. So for livermorium 3+, the angle will be K multiplied by 3 over 292. You get this value. Fl2 minus the angle is K multiplied by 2 over 289. You will get this value. In both cases, K just represents the proportionality constant. So from this, we can deduce that Fl2 minus is actually deflected by a smaller angle than Lv3+. Third statement, from the data booklet, we note that flerovium is group 14, and thus the valence shell electronic config is Ns2np4. Livermorium is group 16 and has Ns2np4 valence shell electronic configuration. And furthermore, these two elements are in the same period, so they have what we call the same number of core electrons. That means the inner shell electrons, both of them have the same number. So when a flerovium atom gains 2 electrons to form Fl2 minus, it will have the same configuration as Lv. This statement will be true. Answer is C, 1 and 3. Question 2, answer here is B. So we are looking at a graph of IE versus number of electrons. And the thing that should stand out the most to you is the big jump from second to third IE, which is indicated on the graph now. And what this tells us is that the third electron was removed from an inner shell. That's why it's much higher in energy. So this element X has 2 valence electrons. It is in group 2, it forms X2 plus cation. So when X2 plus combines with O2 2 minus, they will combine in a 1-to-1 ratio so that the compound is electrically neutral. So the compound is XO2. Question 3, cyanamide forms a product with BF3. So the answer here is A. To answer this question, we need to find out the properties of these two compounds. So BF3 is a Lewis acid. It is electron deficient because the B only has 6 electrons. It has a vacant orbital to accept a lone pair of electrons. Whereas cyanamide is a Lewis base because it possesses lone pairs on both N atoms that it can donate to a Lewis acid via dative bonding. So what happens when they react is that the cyanamide will use one of its lone pairs to form a dative bond to empty orbital on the B atom in BF3. So in this diagram, it shows the lone pair on the cyanide N being donated. But in actual fact, we can also donate the lone pair on this end. Question 4, we are looking for compounds with the same shape and similar bond angles. So it's a straightforward question. It's just testing you on your application of VSEPR. So answer here is A, both compounds are tetrahedral. So for B, AlCl3 is trigonoplanar, NCl3 is trigonopyramidal. For C, sulfur dioxide is bent or V-shaped, carbon dioxide is linear. For D, ClF3 is T-shaped, whereas SF4 is seesaw. Question 5. We are looking for the pairs where first substance has a lower boiling point than the second substance. The answer here is A, because for A, the first alcohol has a smaller size than the second alcohol, even though both of them can do hydrogen bonding. What this means is that there are less electrons in the first molecule, and when they are polarized, it forms weaker ID-ID interactions, which require less energy to overcome. So remember, for contrasting boiling point, we need to mention the energy to overcome the intermolecular forces based on the strength of the intermolecular forces. Okay, option B, iodine is a solid at room temperature, whereas HCl is a gas at room temperature. So it already tells you that this one has a higher boiling point than this one. Option C, this first substance is an amine, so it can do intermolecular hydrogen bonding, which are stronger than PD-PD interactions for between molecules in substance 2. For D, ethanoic acid exists via dimers, where two molecules are bonded to each other via intermolecular hydrogen bonds. So for ethanoic acid compared to ethanol, there is a larger extent of hydrogen bonding. Question 6. Silicon carbide, shiny, hard, inert, and high melting point. So what structure explains these properties? The answer is A. So first thing, okay, this is a covalent substance because both are non-metals. But the fact that it has high melting point, it points towards a giant covalent structure rather than simple molecular. But giant covalent, the structure can be similar to diamond or graphite. But now we look at this part, we know that this silicon carbide is hard, so it means that it is structurally more similar to diamond than graphite. Question 7, we need to find the percentage yields of each step. Answer is B. So we're going to look at each step to find the percentage yield. So for the first step, the amount of sodium sulfide which I used is the mass divided by the MR, 640 moles, which means that theoretically, I should also get 640 moles of sodium carbonate because it is a 1-to-1 stoichiometry. So we let the yield of sodium carbonate here be Y, and the actual yield of sodium carbonate will be 640 Y moles. Then we'll move this here. So now we are starting with 640 Y moles of sodium carbonate in step 2. The amount of sodium hydrogen carbonate that we obtained is 244 moles. And the theoretical yield of sodium hydrogen carbonate from 640 Y moles of sodium carbonate is times 2. So 1280 Y moles. So the percentage yield for step 2 is the actual yield divided by the theoretical yield, which is written as 244 over 1280 Y. And then question specifies each step has the same percentage yield, so I will equate this Y and this fraction. I will get Y squared equals to 0.191 and Y equals 0.437, which means that each step has a yield of 43.7%. Question 8, we have WDM cube of butane. When I burnt, it used this mixture of compounds. So what we're going to do, we are going to try to write an equation that captures this information. So the answer here is B, 6W. So this is the equation that we're going to write. So butane, C4H10, plus X moles of oxygen gives me these products. So the first thing we're going to do is to balance the H on both sides. There's 10 on the reactants side. There's 2 here. So I'll multiply the product side by 5. And then now my products side has 5 plus 1, 6, 6 plus 6, 12. So my product side has 12 oxygen. I will need to balance the reactant side by multiplying the the O2 by 6, which means that X is 6. So since all of these species are gaseous, the volume is proportional to the amount of gases. So which means that if I want to, 1 mole of butane reacts with 6 moles of oxygen. So this one is the same as saying 1 dm cube of butane is burnt in 6 dm cube of oxygen. So if I have W dm cube of butane, naturally I will need 6W dm cube of oxygen. Okay, question 9. Answer is C. So if you count the if you interpret the skeletal structure, the formula for glucose is C6H12O6. Then I'm going to remove all the alcohol groups attached directly to the ring carbon atoms. So there are 4 hydroxyl groups that are removed. So it becomes C6H4O2. Then I will put in 4 chlorine atoms. And this is the formula now, C6H8Cl4O2, which gives me the empirical formula of C3H4OCl2 or C3H4Cl2O. Okay, question 10. Now this type of question should not be unfamiliar to you by now. So our general strategy is always to find the amount of electrons transferred. So we start with zinc. Okay, the amount of zinc used is mass divided by molar mass of zinc, which is 65.4. And this is the amount of amount of zinc that we are using in this reaction. When zinc is oxidized, it loses 2 electrons, which means that the amount of electrons lost by zinc in this reaction is this number multiplied by 2. Okay? Next, we look at VO2+. The amount of VO2+ is concentration times volume, is this amount. So amount of VO2+, the ratio of the amount of VO2+ to the amount of electrons is this to this. If you simplify, it becomes 1:3. So each vanadium atom in this species will gain 3 electrons. And if you find the original oxidation state of vanadium in VO2+, it is plus 5. Each V atom gains 3e, and when there is a gain of electrons, it corresponds to a reduction in the oxidation state. So the final oxidation state of vanadium will be plus 5 minus 3. The final oxidation state is plus 2, which corresponds to the species of V2+. Next, we move on to question 11. We are given enthalpy changes of combustion and we are told to find the enthalpy change of the given reaction. The long way for this question involves drawing energy cycle, but since the question is nice enough to give you the enthalpy change of combustion for everything for all the species in this equation, you can use a shortcut. But before that, the answer for this question is B. So what is the shortcut? Okay, the shortcut is that the enthalpy change of reaction is the sum of the enthalpy change of combustion of reactants minus the sum of the enthalpy change of combustion of products. Okay, so our reactants, the sum of enthalpy change of combustion is negative 283 for CO plus 2 times negative 286 for hydrogen. My enthalpy change of combustion of products is negative 715. So I'll just press this to the calculator. Answer is negative 140 kilojoules per mole. So something that is related, okay, if question didn't give you enthalpy change of combustion but gave you enthalpy change of formation, you can apply a very similar equation, which is that enthalpy change of reaction is the sum of the enthalpy change of formation for products minus sum of enthalpy change of formation for the reactants. Question 12. We want to measure the temperature change when 2 grams of magnesium chloride is dissolved in 50 grams of water. So for this, we will need to find the enthalpy change of solution of magnesium chloride first. Okay, and to do that, we will need to construct the energy cycle. So the answer here is B, plus 13.3 degrees Celsius. So how do we form the energy cycle? We are going to start with MgCl2 solid, and then we absorb 2526 kilojoules per mole of energy and break it up into gaseous ions. This is essentially the reverse of the lattice energy of magnesium chloride. Then from these gaseous ions, I'm going to hydrate the ions. So to hydrate magnesium ion, negative 1890, to hydrate 2 chloride ions, will be 2 times negative 384. So hydration is exothermic because it involves forming ion dipole interactions between the ions and water molecules. So I end up with aqueous ions. Then to complete the energy cycle, this arrow represents my solution, the enthalpy change of solution for solid magnesium chloride. Okay, so I apply Hess law. The enthalpy change of solution for magnesium chloride is 2526 plus negative 1890 plus 2 times negative 384 will be negative 132 kilojoules per mole. Which means that when I dissolve 1 mole of magnesium chloride in excess water, I will release this amount of energy. So when 2 grams of magnesium chloride is dissolved, the energy released is, in joules, would be the enthalpy change of solution. I multiply by 1000 to convert it to joules, and then multiply by the amount of magnesium chloride, mass over molar mass, will be 2770 joules. And then I will use this and sub it into a rearranged form of Q equals mc delta T. So my delta T, or my temperature change, is Q divided by mc, will be 2770 divided by 4.18, which is the heat capacity of water, multiplied by 50, which is the mass of water. So the change in temperature is 13.3. And since this is exothermic, so it will be a gain of 13.3 or plus 13.3 degrees Celsius. Question 13. Again, we need to evaluate the statements. The answer here is A. Okay, so statement 1, the enthalpy change of reaction. This is where we use the equation that we mentioned in question 11. So enthalpy change of reaction is the sum of enthalpy change of formation of products minus sum of enthalpy change of formation reactants, which will be negative 1273 minus formation of 6 carbon dioxide plus the formation of 6 water, which is positive 2807 kilojoules per mole, which means statement 1 is true. So statement 2, system becomes less disordered. So this statement is talking about entropy change. So on my reactant side, I have 6 moles of gas and 6 moles of liquid. But on my product side, I have 1 mole of solid and 6 moles of gas. So there are less ways to arrange the particles for the products than the reactants, which means that after the reaction, the system had become less disordered. So 2 is correct as well. So for statement 3, we need to combine statement 1 and statement 2 using the equation delta G equals to delta H minus T delta S. So since my delta H is positive and delta S is negative, so regardless of the temperature, my delta G will always be positive. So regardless of temperature, my reaction is always non-spontaneous. That's why all 3 statements are correct. Okay, question 14. So we have a graph of the volume of KMNO4 used to titrate against hydrogen peroxide over time. So first thing, we note that the volume of KMNO4 used is proportional to the concentration of H2O2, because the H2O2 is the concentration of H2O2 is proportional to the amount, which is in turn proportional to the amount of KMNO4 mentioned in the question. Second thing, if you look at this graph, okay, it shows a constant half-life where the volume of KMNO4, the time taken for volume of KMNO4 to decrease by half, which is from 13 to 15, is 14 minutes. To decrease from 15 to 7.5 minutes is also 14 minutes. So the decrease in KMNO4 has a constant half-life, which means that the decrease in concentration of H2O2 also follows the constant half-life, which suggests that it is first order with respect to H2O2. Okay, so now that we have this, okay, we need to find the initial concentration of H2O2 to find out how much time has passed from the original concentration of 3 moles per dm cube. So initially we used 30 cm cube of KMNO4. Concentration of KMNO4 is 0.05. So the amount of KMNO4 to oxidize hydrogen peroxide is this amount. So the amount of H2O2 will be this amount divided by 2 times 5. And the concentration is the amount of H2O2 divided by its volume, which will give me 0.375 moles per dm cube. So when I started the reaction, the concentration of hydrogen peroxide is 0.375 mole per dm cube, but my starting concentration was 3 moles per dm cube. So how many half-lives have passed? So starting with 3, after the first half-life it became 1.5, second half-life 0.75, third half-life would be 0.375, which means that 3 half-lives have passed before I started my reaction. Half-life is 14 minutes, so the time elapsed is 42 minutes. Answer is C. Okay, question 15. Rates of chemical reaction, how is it affected by concentration or temperature? So the answer here is D. Okay, and to explain why it's D, I'm going to use something that is not in syllabus and is only for your knowledge, but this equation will explain to us how to change the rate constant. Okay, so this is called the Arrhenius equation, and the important letters inside here, K is the rate constant, EA is activation energy, and T is temperature. So what this tells us firstly is that the only two factors that can influence the rate constant of a reaction are temperature, and secondly is to change the activation energy by using a catalyst which provides alternative pathway that has lower activation energy. So when I change temperature, I change the rate constant. When I change concentration, it has no effect on rate constant. Okay. Next, the kinetic energy that particles possess is affected only by its temperature. When I change the concentration, it does not affect the kinetic energy of particles, which means 2 is false, 4 is true. Okay, question 16 is a mechanism question. Okay, which option describes the rate equation? So this is a multi-step process. Okay, the answer here is B. For a multi-step process, the rate equation is that of the slow step, otherwise known as the rate determining step. So based on the slow step, this is my rate equation. Rate equals to K N2O2, K times the concentration of N2O2 times concentration of H2. But N2O2 is an intermediate. We do not expect to see it in the rate equation. So the rate of forming N2O2 in turn is dependent on this fast step 1, which produces it. So we need to replace it with the reactants in step 1. And since the concentration of N2O2 is directly proportional to the concentration of NO squared, so we can rewrite this as concentration of N2O2 equals to K1 multiplied by concentration of NO squared. So we can rewrite this rate equation as rate equals to K1 NO to the power of 2 and H2. So the answer is B. Question 17, answer is A. So you can do it in one step, but I'm going to explain how. So firstly, okay, M contains helium at a certain pressure and certain temperature. After I open the valve, M is combined with N, and N has 3 times the volume of M, which means that the total volume in this container now was 4 times the original volume. And we know that pressure is inversely proportional to volume, and since my volume is expanded 4 times, my pressure will be decreased by 4 times. So my new pressure is this one divided by 4, which is 2.5 times 10 to the power of 4 pascals. And then next I place this in boiling water. The temperature increases from 25 degrees Celsius to 100 degrees Celsius. Common mistake here is when you fail to convert, but always remember when we're dealing with gases such as PV equals nRT, temperature is always in kelvins. So the temperature changes or increases from 298 to 373, which is 1.252 times. So my new pressure would be this times 1.252, because pressure is directly proportional to temperature. So my final pressure is this, which is A. Let's move on to question 18, where we are asking you on the Haber process. So which graph describes how the yield of ammonia at equilibrium changes as pressure increases? Answer here is D. So We know that Le Chatelier's principle predicts that increasing pressure favors a reaction which produces less particles of gas to reduce the pressure in the system. So looking at the equation for synthesis of ammonia, you're going to notice that the forward reaction produces less particles of gas. So that makes it favored when the pressure is increased. The position of equilibrium will shift right, and the equilibrium yield of ammonia increases. Okay, question 19 on chemical equilibrium. Answer is A. So we construct our ICE table and we're going to put in numbers that the question has given to us. So the question has told us that the initial amount of N2O4 is 1 mole. Initial amount of NO2 is 0.2 moles, and the equilibrium amount of NO2 is 0.68 moles. So from there, we can calculate that the change in the amount of NO2 is 0.48. And from here, we can calculate the change in the amount of N2O4, which will be negative half of this, which is negative 0.24, because NO2, the amount will be twice the amount of N2O4, so the change is also proportional to that. And finally, the equilibrium amount of N2O4 is 0.76 because it's 1 minus 0.24. So now that we have the amounts of these two species at equilibrium, we can write our Kc expression. Remember that we have done our ICE table in moles, but Kc is calculated in terms of concentrations. So we need to divide by the volume of the container when we calculate Kc. So the Kc value is 0.15. Question 20. Which mixtures represent Bronsted-Lowry acid and its conjugate base? The answer is B. So recall that a Bronsted-Lowry acid is a proton donor. The conjugate base of a Bronsted-Lowry acid is the species that is formed after the Bronsted-Lowry acid has lost a proton. Okay, so we're going to look at these mixtures and see what happens when they dissociate in water. So for example, we know that water, H2O, when it undergoes autoionization, it produces H plus and OH minus. So this tells us that when water acts as a Bronsted-Lowry acid, the conjugate base left behind is the OH minus ion, which means that for number 1, it is a mixture of a Bronsted-Lowry acid and its conjugate base. Similarly, for the second one, we have H2PO4 minus. It dissociates to form H plus and HPO4 2 minus ion. So again, this one is a mixture of Bronsted-Lowry acid and its conjugate base. The third one, NaH and Na. So first thing, note that NaH is an ionic compound. It contains Na plus ion and H minus ion, which is known as hydride ion. So when it dissociates, for example, when you melt NaH, you produce H minus ions instead of H plus ions. So therefore, we cannot say that NaH can behave as a Bronsted-Lowry acid. So the only mixtures that have a Bronsted-Lowry acid and its conjugate base will be number 1 and number 2. Okay, questions 21 and 22 are not tested for promos, so we will move on directly to question 23. With the molecule given below, which statements are true? Answer is B. So statement 1, there are 4 sp2 carbons in the molecule. This is true. The sp2 carbons are circled in purple, in pink on the screen. Second statement, the pi bond between C3 and C4 is formed by 2p2p overlap. Okay, this is also true. So we note that C3 and C4 is a carbon-carbon double bond. So there is one sigma bond formed by sp2sp. It's a sp2sp overlap. whereas the pi bond is formed by a side-on overlap of the unhybridized 2p orbitals present in each of the carbons. Third statement, sigma bond between C1 and C2 is longer than between C4, C5. So the sigma bond between C1 and C2 is formed by head-on overlap of the sp2 orbital on C1 and the sp2 orbital on C2. Whereas for C4, C5, the sigma bond is formed by overlap between sp2 orbital on C4 and sp3 orbital on C5. So what you need to recall is that when a CC single bond is formed from hybrid orbitals with a higher percent of S character, so for example, sp3 hybrid orbitals have 25% S character, sp2 has 33% S character, sp has 50% S character. So when a bond is formed by hybrid orbitals with higher percent of S character, it makes the bond shorter because electrons in a hybrid orbital with higher percent of S character will be closer to the nucleus, which makes it feel the attraction of the nucleus more strongly. So which means that the C1, C2 sigma bond will actually be shorter than the C4, C5 sigma bond, which means statement 3 is false. Okay, question 24. A non-cyclic organic compound is C5H8O2, which functional groups cannot be present in the molecule. The answer here is D. So to explain why it's D, I need to bring in a term called the degree of unsaturation, which measures the number of pi bonds in the molecule. And it's important to note that the presence of oxygen atoms does not affect the degree of unsaturation in a molecule. So to illustrate this, we have a 5-carbon alcohol as well as a 5-carbon alkane. You're going to notice that the alcohol is saturated and it contains the same number of hydrogen atoms as the 5-carbon alkane. Okay, so this tells us that even with or without oxygen, the number of pi bonds in the molecule is not affected. So we can treat this C5H8O2 as C5H8, and you'll notice that compared to the saturated C5 alkane, which is C5H12, this molecule is 4 hydrogens short, which means that this molecule contains 2 pi bonds. So our functional group combinations must contain 2 pi bonds. Okay? So for number 1, alkene has 1 pi bond. The carboxylic acid group also has 1 pi bond. So this combination is possible. Secondly, ketone has 1 pi bond, alcohol has no pi bonds, which means that there's only 1 pi bond, so this is not possible. Thirdly, aldehyde and ketone, so each carbonyl group have 1 pi bond each, so this is possible. Lastly would be alkene and 2 alcohols. Alkene only has 1 pi bond. Each alcohol does not contain a pi bond, which means that we are again short of 1 pi bond. So answer is D. Question 25. How many possible non-cyclic isomers are there with molecular formula C3H5Br? Answer is C. So first thing, we know that C3H5Br, it is derived from propene, which is C3H6. So you can perceive it as propene, where one of the hydrogens is replaced by bromine. So this is the structure of propene. You'll notice that we can replace the hydrogens at 3 different spots to give 3 different mono-bromo compounds. So this is one. If I replace the CH3, one of the hydrogens with a Br, I get the second isomer. And thirdly would be this. And you notice that this third one, okay, each carbon has two different groups attached to it, which means that it can exhibit cis-trans isomerism. So total there are 4 isomers including stereoisomers. Next, compound U undergoes substitution with chlorine gas to form mono-substituted compounds. So again, you need to find the number of types of H atoms in this molecule U. So the answer is 6. So firstly, if I replace one of the H's on the methyl group with a Cl, I get this isomer. Secondly, the carbon which bears a methyl group also still contains a H. So I can replace the H with a Cl to get the second isomer. And next, okay, the other carbons on the cyclopropane ring contain a H. I can replace a H with a Cl. And you notice that for this one, there are actually 2 chiral centers, which means that there are a total of 4 stereoisomers for this compound. So the total number of isomers, including stereoisomers, is 6. That's 1, 2, and 4 for this isomer alone. Okay, question 27. It is a pattern recognition question. So first we mentioned that epoxyethane, it forms a double-ended free radical, and this double-ended free radical reacts with another molecule of epoxyethane, and it keeps adding on to subsequent molecules of epoxyethane. So the first thing to notice, okay, is that every propagation step continues to produce double-ended radicals that have an increasing number of CH2-CH2O groups. Or you can say that this CH2-CH2O group is a repeating unit. You'll see this multiple times in a molecule of the non-ionic detergent. So therefore, the detergent should contain this structural feature, CH2CH2O-N in its structure, which means that A is wrong because it does not contain such a structure. So the second piece of information is that termination of the chain occurs when a double-ended free radical reacts with alcohol to form a non-ionic detergent. So the detergent should contain the same number of atoms as an alcohol, and alcohols have this general formula, CnH2n plus 1 OH. So both B and C are wrong because they contain additional oxygen atoms more than the typical alcohol. So the only possible answer here would be D. Okay, question 28. We have compound V. What happens or what products are formed when V is heated with excess hot acidified KMnO4? So this is oxidative cleavage. The answer is D. So I've drawn out the oxidative cleavage here. So this double bond circled in purple, it becomes propanone. So CH3COCH3, and the remaining part forms the big molecule. Next, this pink double bond, there is a CH2 group here, which means that after oxidative cleavage, it becomes carbon dioxide and water. And what is left behind is this big molecule. This side becomes a carboxylic acid here. This part becomes a ketone. And this cyclic alkene becomes a ketone on this side and a ketone on this side. The ketone groups in the product are separated 1, 2, 3, 4, 5. So it is a 1,5 diketone structure that is found in the product. Okay, question 29. The answer here is A. Okay, so we have cyanogen bromide, which undergoes addition reactions with alkenes, and we note that with propene, it forms isomer D rather than E. So this should remind you of Markov-Nichols rule, which applies when we do electrophilic addition to alkenes. So in this case, we need to modify the Markov-Nichols rule a bit, where the electrophilic part of the cyanogen bromide molecule will go to the carbon atom in a double bond which had more hydrogen atoms to begin with. So in propene, we are referring to carbon 1, which had 2 hydrogen atoms to begin with. So the part of the cyanogen bromide molecule which added to this carbon is the electrophile. Okay, so we note that isomer D is formed, which means that the bromine is the electrophilic part of the molecule, and the intermediate is a carbocation which contains the bromine atom. So similarly, okay, when we add cyanogen bromide to this alkene, okay, the bromine will attack to the second carbon first, and it leads to the formation of a carbocation on the adjacent carbon, which is then attacked by the Cn- nucleophile to form the product. So the answer is A. Next, question 30. We have compound X with the following structure. It undergoes reaction to form Y, which has the same number of chiral centers as X. Okay, so we need to identify where and what number of chiral centers are there in X first. So in X, there are 4 chiral centers indicated here, which means that after reacting X with the appropriate reagents and conditions, we should still have 4 chiral centers. So first one, when we react X with coalkaline KMnO4, we are oxidizing the carbon-carbon double bond into a diol. Okay, so when this happens, okay, it forms this diol as a product. The number of chiral centers now becomes 5. So there is an increase in number of chiral centers. Okay, next, Al2O3 heat, this reaction would be elimination of water from the alcohol, and it forms 2 products as a mixture of isomers, but both of these isomers will only have 3 chiral centers. So B is also not the answer. C, we have Br2 dissolved in CCl4 at room temperature. So this is electrophilic addition of bromine to the CC double bonds. The product has 5 chiral centers. Lastly, H2 and nickel heat. This is reduction of the double bond, the CC double bond to alkane. So the product looks like this. It also still has 4 chiral centers. So the answer will be D.